In this video, we will talk about particles, antiparticles, their mediators, the standard model, the forces between particles, and stuff like that. So, the standard model which is currently the state-of-the-art description of the universe we have. So, the standard model describes all particles, antiparticles, and mediators in the universe. So let's try to make a brief tree of all particles, if that makes any sense. So we have, in the universe, we have particles and their corresponding antiparticles. And we've seen many examples of that. The proton and the antiproton are an example of a particle-antiparticle pair, the electron and the positron, etc. When these two meet, they annihilate into light. And this is a consequence of E equals mc squared, of the fact that matter and energy are interchangeable. But anyway, so particles and antiparticles can be split into two broad categories, okay? The first category is called hadrons. Hadrons are composite particles and are made of quarks. Okay, and hadrons, since I'm Greek, comes from the Greek, ancient Greek word adros, which means heavy. Okay, and then leptons, which are fundamental particles. Okay, fundamental particles, meaning that they don't have a structure. Okay, now leptos in Greek means light, and leptons are supposed to be light particles. So examples of leptons are, let's use green, the electron, the muon, we will talk about these things, the positron, the electron, neutrino, etc. And examples of hadrons are the proton, the pion, the neutron, etc. Now, hadrons also split into two more categories, and I ran out of space here, so I'm gonna come here and maybe do this. Let's see, does this work? So yes, so we have two more families of hadrons. We have the mesons. Again, this is a Greek word which means in between. Okay, meson means in between. Okay, because they are supposed to be particles that are in between a very heavy particle like a proton and a very light particle like the electron. So mesons consist of quark plus antiquark pairs. And then we also have the baryons, from the Greek word varis, which means heavy. Baryons always consist of three quarks. Don't worry, we're going to talk about quarks and everything soon. All right, so we covered particles and antiparticles, right? But remember, when we started talking about this, we talked that the standard model describes particles, antiparticles, and mediators. So what are mediators? Let's go talk about them and define them briefly too. So mediators are, I'm going to write in parentheses here, they mediate forces between particles. Okay, there are four mediators in the universe, and this is because there are four forces in the universe. Okay, so the first mediator is the mediator of electromagnetism, which is the photon. So gamma is the photon. It's the mediator of electromagnetism. Then the electromagnetism is one of the forces in the universe. Okay, then we have the W plus, minus, and Z naught bosons. This is how they are called. And by the way, the photon is massless. The mass of the photon is 0. So then these 3 particles, the W plus, the W minus, and the Z naught, are the mediators of the weak force mediators. Okay, the third one, the third mediator, and these are massive particles, so they have a mass. Then we have the mediator of the strong force, which is called gluon. Okay, so gluons, this is how they are called. They are mediators of the strong force, and they are also massless. And finally, what's the fourth force in the universe? And it's kind of like the only one we experience in everyday life. It's gravity, right? So gravitons are the mediators of gravity. They are expected to be massless, but they have never been found and nobody knows what they are and what they look like. But they are expected to be mediators, okay, of gravity. Now, this is optional, so I'm going to write it down here, optional. So what do we mean by mediator? So let's say we have an electron, okay, interacting with another electron, okay, so both come in, and then if they move in this direction, they will repel each other, and this guy will go to the left and this guy will go to the right, okay? So the idea of the mediator is that this repulsion happens because, let's use yellow, is this visible? So the idea is that photons are exchanged between these two guys, and it's because it's like, imagine being in a boat and there is a friend of you in another boat in a lake, okay? And then you throw a massive ball towards each other. Eventually you will start moving because of the conservation of momentum, right? So the idea is the same here. The electrons come in, okay? They exchange a photon, and that photon pushes the other electron out, okay? So that's the idea. This is, by the way, a Feynman diagram. This is really advanced for high school students, but this is what the current theory tells us. Okay, now let's move to quarks and leptons. There are 3 generations. There are 3 generations of quarks and leptons. As far as I know, this is something that is expected of you to know. Okay, so let's start with leptons and the 3 generations of leptons. So leptons, first generation is the electron, and I'm gonna run out of space if I write it like this, so let's move this there. So okay, we have the electron and the electron neutrino. The charge is -1 for the electron, and the charge of the neutrino is 0. The mass of the electron is 0.5 MeV over c squared, and the mass of the neutrino is about 0. Okay. There's something I don't like here. I don't have enough space. Maybe I'm gonna erase this and edit it out. And yeah, let's write it again. So there are 3 generations of quarks and leptons, as we said. So let's start with leptons. Okay, generation 1 is the electron and the electron neutrino. The charge is -1 for the electron and 0 for the neutrino. The mass is 0.5 MeV over c squared for the electron, and it's about 0 for the electron neutrino, though it's near 2.2 times 10 to the -6 eV over c squared. Okay. Why did I write mass as MeV per c squared? Because energy is mass times c squared. And remember that if I take the mass of an electron, say, which is 9.1 times 10 to the -31 kilograms, and convert this into energy, I will find that the energy is 0.511 MeVs, okay? But since energy is mc squared, and since 0.5 MeVs corresponds to the rest energy of an electron, I can also write that mass is energy over c squared. So that's 0.511 MeV per c squared. I hope this makes sense. Okay, now generation 2. And by the way, these generations correspond to the historical discovery of these particles. So the electron and the electron neutrino were the first to be found. And then the muon and the muon neutrino were found. So the muon is like the heavier cousin of the electron with a charge of -1. The charge of the muon neutrino is also 0. The mass of the muon is 106 MeV over c squared, so it's heavier than the electron, much heavier actually, 200 times heavier. The mass of the muon neutrino is also thought to be 0, but it's something like less than 0.17 MeV over c squared. And finally, the third generation, which was discovered in the 90s, so kind of recently actually. Was it the 90s? Maybe yeah. You don't need this information, but it was recent. Okay, is the tau minus and the muon and the tau neutrino. Sorry. So they have charge of -1 for the tau lepton. The mass is really heavy, 1780, so 1780 MeV over c squared, and the tau neutrino is expected to have 0 mass, but it's a matter of debate. So let's take the mass to be less than 20 MeV over c squared. All right, now let's talk about the 3 generations of quarks. So quarks. There are 6 flavors, as they are called, of quarks. So the first generation is the up and down, written as U and D. Okay, the charge of the U is +2/3, whereas the charge of the down is -1/3. So the flavor refers to up and down. So up is one flavor, down is another flavor. Okay, the mass is 0.0023 GeV over c squared, whereas for the down is 0.0048 GeV over c squared. You're not expected to know the masses, but you are expected to know the charges. Okay, so the second generation is the strange and charm, written as S and C, so 2 more flavors. Charge of the Q of the strange is -1/3. The charge of the charm is +2/3. And the masses are, let me see, 0.095 GeV over c squared and 1.27.5 GeV over c squared. And the third generation, 1, 2, 3, is the bottom and up. So B and T, the charge is -1/3, the other charge is +2/3. And these are massive, so 4.19 GeV over c squared and 173 GeV over c squared. All right, that was a lot, actually, more than I expected. Now, how do we build baryons? Okay, baryons. So they are built using 3 quarks or 3 antiquarks. Okay, not a combination. It has to be 3 quarks or 3 antiquarks. So let's do the example of a proton. We know that the proton has a charge of +1 and it consists of up and down particles, quarks, right? So how can we build a proton with 3 quarks so that the charge is 1? We need 2 ups and 1 down, right? 2/3 plus 2/3 is 4/3 -1/3, we get 1. So UUD. Okay, so the charge is 1. Now I'm going to introduce new numbers. The baryon number of the proton is 1. The lepton number is 0. And the strangeness is 0. Okay, so the baryon number comes from the quarks only. The lepton number it's only there when we deal with leptons. And the strange number is related to the s quarks, so has no s quarks. So what I'm trying to say is that since the proton has no s quarks, its strangeness is 0. Now let's build the antiproton. We use this bar on top of P. So we need the 3 anti-quarks now, okay? So U bar, D bar, charge is -1. The baryon number is -1 now. Remember, this is something we haven't talked about, but particles and antiparticles have exactly opposite numbers. So you see how the charge of the proton is 1, for the antiproton is -1. The baryon number is 1 for the proton, so it's -1 for the antiproton. Now the lepton number and the strangeness is 0 for the proton. It's the same for the antiproton, since the antiproton obviously has no leptons and no strange quarks, okay? Now let's talk about lambda 0. This is a baryon that consists of a U quark, a D quark, and an S quark. So the charge is 2/3, -1/3, -1/3, so that's 0, right? The baryon number is 1 because it's 3 quarks. Every quark carries a baryon number of 1/3, okay? So 3 times 1/3 gives you 1. Every anti-quark carries a baryon number of -1/3. So this is 3 times -1/3 equals to -1. And yeah, the same for the proton. Now the lepton number is 0 for lambda 0 because no leptons are there, but the strangeness is -1, okay? Because it has 1 s quarks. So what are the rules? How do we find these numbers? So strangeness is defined as the negative of the number of strange quarks in a particle minus the number of anti-strange quarks, okay? The baryon number is 1/3 times the number of quarks minus the number of anti-quarks, okay? And the lepton number is equal to the number of leptons minus the number of anti-leptons, okay? That's it. Simple. Now, let's talk about mesons. Maybe I'm going to use a clean page, okay? So, mesons, they consist of a quark anti-quark pair. So, let's go see some examples. The pi plus consists of a U and a D bar. So, the charge is 2/3 plus 1/3, so +1, okay? The lepton number is 0, baryon number is 1/3 -1/3, so 0, and strangeness is 0, okay? Now pi minus consists of a U bar and a D, so the charge is -1, the lepton number is 0, the baryon number is 0, and the strangeness is 0. Now let's talk about an interesting case. So K plus consists of a U quark and a and an S bar quark. So the charge is +1, the lepton number is 0, the baryon number is 0, and the strangeness is +1 because it consists of an anti-quark, right? And let's go see a very weird example. So the phi meson consists of an S quark and an S bar quark. So the charge is 0, the lepton number is 0, the baryon number is 0. What's the strangeness? It's also 0 because we have a pair of strange and anti-strange quarks, okay? Now, let's talk about leptons a little bit. So the electron has a charge of -1, a lepton number of +1, and baryon and strangeness equal to 0. Then the anti-quark has a charge of +1, a lepton number of -1 because it's an anti-particle of the electron, okay? And the other two numbers are 0, okay? Now the the electron, neutrino, there is no muon, has a charge of 0 and the lepton number of +1, okay? Same as the electron. And then baryon number and strangeness equal to 0. and so on and so forth. I don't want to write more examples because it's getting tedious. So we're gonna see later how these guys interact. Okay. Now let's go talk about particles, forces, and reactions. So particles, forces, reactions. So particles, I already hinted towards this direction. So particles interact by exchanging bosons, which are called exchange bosons, and are the mediators we talked about in the beginning. Now about forces, so all particles, actually all massive particles is the correct way to write this, all massive particles experience gravity via the exchange of gravitons. And this force is always attractive, okay? And now leptons experience electromagnetic and weak interactions only. The electromagnetic interactions are mediated with photons, and the weak interactions are mediated by the W plus and minus and the Z not bosons. We already talked a little bit about how this exchange of mediators happens. So for example, if we have an electron interacting with an electron, and then we have an electron going out and another electron going out. The way this happens is we have an electron coming in and another electron coming in. Okay, they exchange a photon. Let's use red. Okay, this is the gamma, and this makes the electrons repel. Okay, and this is a Feynman diagram, by the way. Okay, so this is an electromagnetic interaction. For example, let's see an example of a weak interaction. So in a weak interaction, maybe we have a neutron decaying into a proton plus an electron plus an electron antineutrino. So the way this happens is to remember that the proton consists of 2 up and 1 down quark, and the neutron consists of 1 up and 2 down quarks. So what happens is that we have a change in flavor, okay, as it is called, because you see how the d quark of the neutron turns into a u quark in the proton. So this happens as follows. We have a d quark and an electron neutrino, okay, coming in. They exchange, let's use blue, they exchange a W minus boson, I'm sorry, and then we have a U quark. So we have the conversion of a D quark into U quark, and we also have an electron going out in this direction, okay? So this is a weak interaction. This is an example of a weak interaction. I'm going to write a note here, though. Note, flavor, so a U turning into a D, a strange turning into, let me see, into a charm, etc. So changing the flavor of quarks, so one type of quark into another, can only occur in weak interactions. So this is a very important job that weak interactions do in the universe. Without them, we wouldn't have different particles pretty much, okay? So that's the function of weak interactions. And finally, hadrons. Okay, so we talked about how all massive particles experience gravity. Okay, so this was the first thing. Then we said that leptons experience electromagnetic and weak interactions, and now hadrons, which are baryons and mesons, experience strong weak and EM interactions. Okay, and of course gravity, since they are massive. Okay, so hadrons participate in everything. Okay, and let's see an example. Maybe we have a U quark coming in and a U quark coming out, and sorry, a U quark comes in and a D quark comes in, and we have a D quark going out and a U quark going out. So this happens with the exchange of a gluon. Okay, so this is a strong interaction. Strong interactions cannot change the flavor of quarks, so we cannot have a U quark turning into a D quark via strong interactions. Okay, only weak interactions can do that. Now let's mention a few more things before moving on. So the strong force is what binds nucleons, and nucleons are protons or neutrons in the nucleus. So what binds the nucleus is the strong force, pretty much. The strong force is repulsive. Repulsive in short distances, attractive near the nucleus, and zero for large distances. Now, if we plot the force in newtons experienced by the nucleons inside the nucleus as a function of the distance inside the nucleus, okay, in femtometers, so let's say this is 0, 1, 2, 3, 4, 5, and this is 6, then it will look like this. Okay, so you see how at short distances here it's repulsive. This means that if we bring two nucleons, maybe two protons or a proton and a neutron closer than 1 femtometer together, they will repulse actually. Whereas if the distance between them is between say 1 femtometer and 3 femtometers, so in this region, they will attract each other. And if they are really far away, like 5 femtometers away, and by the way, 1 femtometer is 10 to the negative 15 meters, so that's a really tiny distance. So if they are 5 femtometers away or more, they don't experience the strong force at all. Okay, so the range of the strong force is about 3 to 4 femtometers, and if R is lesser than or about equal to 0.5 femtometers, we get a repulsion between the particles. Okay. Now the weak force has a range of 10 to the negative 18 meters. Okay, so it occurs only inside the nucleus pretty much. So it is responsible, and we already mentioned this, for changing the flavor. And the flavor, as you saw, is the type of quarks or leptons. Okay, that's another thing I didn't mention it earlier. Okay, so for example, if we have a neutron interacting with an electron neutrino, these might produce a proton and an electron. If we have a muon decaying into an electron plus a plus a muon neutrino, muon can decay into an electron plus a muon neutrino plus an electron antineutrino. Okay, so both these procedures, both these interactions are weak interactions because we have the change of a neutron into a proton, for example, here, or a muon into an electron. So So we see how we change the flavor of the lepton here and the flavor of the baryon here, okay? So that's that. And finally, the electromagnetic and gravitational interactions have infinite range. Okay, so we saw how the weak force is only experienced within the nucleus, same as the strong force, but electromagnetism and gravity can be felt from a distance, from infinite distance as well. So now the next thing, and almost the final, is the particle interactions. So particle interactions, we have already seen a lot of examples, but let's go make it concrete. So the rules: in all interactions, charge, lepton number, and baryon number are conserved. So for example, we cannot have a proton decaying into a positron and an electron neutrino. So that cannot happen. Why? Because we have a baryon number of 1 on the left-hand side and a baryon number of 0 on the right-hand side, and so on and so forth. So this is forbidden. Second rule: strangeness is conserved only, that's why I'm capitalizing it, in strong interactions. And also electromagnetic interactions. So we can also say that strangeness is not conserved in weak interactions. Okay, so let's see an example. A pion interacting with a proton gives a positive kaon, this is how it's called, plus a negative kaon plus. And so on the left hand side we have a proton, so the baryon number is 1. On the right hand side we have a neutron, so the baryon number is also 1. The charge is 0 before and after, right? The lepton number is 0 because we have no leptons, and we have no leptons after. And the strangeness is 0 before, and after we have the kaon has a strangeness of 1, but the negative kaon has a strangeness of -1, so we have 0. So this is a strong interaction, okay, because strangeness is conserved. Now let's see another example: the decay of a positive kaon into a positive pion plus a neutral pi. So the baryon number is 0 before and after. The charge is 1 before and after. The lepton number is 0 before and after. But the strangeness is 1 before and 0 after. So this is a weak interaction. This is a weak interaction pretty much. So this reaction proceeds via the weak force pretty much, okay? Because it violates strangeness. So in strong interactions and electromagnetic interactions, strangeness is conserved. So because it's not conserved, we know immediately that this is an example of a weak interaction. I hope this makes sense. So again, I'm going to write it down as a rule: weak interactions change the flavor of quarks and leptons. Okay, finally, strong interactions are fast, so they happen really fast in about 10 to the negative 23 seconds. Weak interactions are slow, so they proceed in like 10 to the negative 10 seconds. And electromagnetic interactions take a time of about 10 to the negative 16 seconds, so they are kind of like in between. Now let's go see some action via examples. So examples, we have the uranium-235 It has 92 protons, right? Decaying into a thorium 231 90 plus an alpha particle. Okay, so let's go see if things are conserved. So the charge before is plus 92, the charge after is also plus 92 because we see it from here, right? Now the baryon number, what's the baryon number? 235, right? Because we have 235 protons and neutrons. And this decays into 231 and 4, so the baryon number after is 235 as well. The lepton number is 0 before and after because there are no leptons involved, and the strangeness is 0 because this is an interaction that involves protons and neutrons, so there are no strange quarks involved. Okay, so this is an interaction that proceeds via alpha decay, which is a strong interaction or an electromagnetic interaction. Now let's go see another example. Carbon 14 decaying into nitrogen 14 plus a beta particle. It has a charge of -1 and 0 and 0 mass number, and an electron antineutrino. So the charge before is 6. The charge after is 7 minus 1, so 6. So charge is conserved. Baryon number is 14 before and 14 after, so that's conserved because the baryon number of the electron is 0, and same for the neutron. The lepton number is 0 before, and the lepton number after is 1 due to the electron, -1 due to the electron antineutrino, so 0, so that's conserved. And strangeness is 0 before and after because there are no strange particles involved. All right, so the final example, which is something we talked about in a different video, is 2 protons colliding, producing 3 protons and 1 antiproton. So let's see, charge is 2 before and 2 after. Lepton number is 0 before and 0 after. Baryon number is 2 before, and after it's 1 plus 1 plus 1 minus 1, so it's 2. And strangeness is 0 before and after. But this violates the conservation of energy seemingly. But remember how when particles move with relativistic speeds, their mass increases. So this is an example of mass energy conservation because energy corresponds to mass. And when particles move at really, really high speeds, they gain mass, so they have more energy. So this reaction can proceed. So mass energy is conserved. So this is a possible reaction. So reaction is feasible. Okay, it can happen. The last topic in this chapter is the muon decay. So we saw earlier that the muon can decay into an electron plus an electron antineutrino plus a muon neutrino, and the anti-muon, the positively charged muon, can decay into a positron plus an electron neutrino plus a muon antineutrino. All numbers are conserved, charge, lepton number, etc. So we're not going to deal with that in this topic. Instead, we are going to mention that this case in with a lifetime of 2 times 10 to the negative 6 seconds or 2 microseconds. Okay, this means that in 2 microseconds, 63% of all muons are gone. Okay, they travel with a speed of about 0.98 the speed of light. Okay, so let's go see how much distance they can cover if they travel with this speed and they decay in 2 microseconds. Okay, so so let's go see how much distance they can cover before they decay. So before decaying, they can cover a distance of L equal to their velocity times their lifetime. So 0.98 the speed of light times 2 times 10 to the negative 6 seconds. And if we plug in numbers, we will find 588 meters. Okay, so if this is the Earth, okay, and the atmosphere of the Earth extends to 10 kilometers, okay, 10 kilometers, and we know that muons come from outer space, so these are the muons. Then once they enter those muons that can enter the atmosphere can only cover about 600 meters before they decay. So we shouldn't see any muons. We shouldn't be able to detect any muons on the surface of the Earth whatsoever. Nevertheless, we can observe plenty of muons on the surface of the Earth. Okay, this is how they were discovered, actually. Okay, so how is this possible? They can only travel up to 600 meters and decay. So all of them should decay before reaching the surface of the planet. So what's the explanation? Recall that particles moving with relativistic speeds, so larger than or equal to about 0.05 c, and in this case they travel with 98% the speed of light. Okay, so particles moving with relativistic speeds move slower. Okay. Sorry. I'm gonna edit this out. So recall that time moves slower for particles moving at relativistic speeds. And relativistic means more than or about equal to 0.05 c. So these guys move with 98% the speed of light. So they definitely move relativistically. So, and even though this is optional, recall, I'm going to write it here, optional, okay, that t prime is equal to gamma t. So the time is 2 times, the time for these guys to decay is 2 times 10 to the negative 6 seconds. And then we have this gamma factor, which is 1 minus 0.98 squared, right? So the actual time that muons take to decay is actually 10.1 microseconds. So they take longer to decay. So L observed is 10.1 times 10 to the negative 6 times 0.98 times 3 times 10 to the 6 meters, right? So they need 2,955 kilometers. So they decay within 3 kilometers, and we can observe them. Okay, so fast particles live longer. Okay, I'm gonna close this video with this, and actually this is the end of unit 4, guys. So we're making progress.